Uh, Hello, everyone. So this is my website, and as John explained, it's in 3D. But the thing I'd like to draw attention to first is the fact that the word math is in the header. And the reason the word math is in this header is because it's really been a constant theme in my work. But more than that, it's kind of my secret weapon, my secret ingredient. Because whenever you take a mathematical approach to your work, you really get a lot of flexibility and power out of it. You can do crazy things like this. And this is localhost, but there's the real website that's running in Safari with CSS 3D. It just kind of works. So that's what I'd like to talk about today. That is not full screen. There we go. All right. Now, you may be wondering why is a presentation with this title standing between you and your beers on Friday? And I wouldn't blame you for wondering that. Because you might think that what we're about to do is something like this. It's not. Not at all. This is quantum mechanics. It's very interesting. But to understand this, you need to take a different approach. What I'd like to talk about instead is stuff like this. Paul Lockhart, who said, I don't see how it's doing society any good to have people walking around with vague memories of math class and clear memories of hating it. And that's true. We're doing something wrong with our mathematics education. And he has a really good example for this, which is you take a box, and inside that box you fit a triangle. And you may be wondering, how much of the box does the triangle cover? You may know the answer to this if you remember your geometry. But the question isn't what is the answer, the question is why is the answer what it is? And there's really only one thing you need to do to solve this problem, and that's draw one line, this line. Because once you've done that, you've created two equal triangles on the left, two equal triangles on the right, which means that the entire triangle covers half of the rectangle. It's a very simple visual proof. Only what we do in school is we reduce it to this, and then we give kids a sheet of triangles, and they have to calculate the area of all of them. And so the question of why do all these triangles happen to have the same area isn't really addressed, and we don't really teach people the background, which is a shame. Second quote by Brett Victor, who Jeremy mentioned as the person who did the talk, Stop Drawing Dead Fish. The power to understand and predict the quantities of the world should not be restricted to those with a freakish knack for manipulating abstract symbols. Mathematics to me is this. This is a JS1K demo that I did. And so in this 1 kilobyte of code that runs on Canvas, you have 3D animation, 3D glow effects, the whole thing. And yet the code is this. And now this is obfuscated. I don't have to tell you guys that. But I don't put it up there so we can try and understand it, but rather to look at the form of this. And there's really two things. One is this isn't a lot of code. There's not a lot of room here. And second of all of these statements are really quite simple. So how do we get something like this out of that? That seems impossible, or at least some serious dark magic. And the answer lies in how these simple pieces all combine. So when you're talking about making things with math, the thing to look at is the systems you put together, and not so much the Legos they're made out of. But I'd like to start, before we dive in, with some background, where this began for me, which was in the Winamp days. I'm sure a lot of people remember this. Winamp was, an MP3 player, was really cool, not just because it had its own custom UI and was quite forward-thinking in that regard, but because it had music visualizations, and you could create these crazy-ass animations that usually move more than this. And you would use a UI like this to do it. And so you type some code, and the thing on the left changes in real time. You type some more code, it shrinks down. And here I paste in another random snippet, and it kind of turns into this weird sort of Phoenix-like effect that was completely unintentional, but it looks cool, looks interesting. And so it really, the fact that it was real time, and between every single keystroke, it updated and showed you the results of that, was key to making this program interesting, and it created a community of enthusiasts who were really into mathematics and came from a background that wasn't necessarily, science or engineering. There was a lot of creative people, designers, who just learned how it worked by playing with it. And so Angus said yesterday, play is what makes code fun, and I think the same applies to mathematics. So I'd like to show you how that works. So take, for example, a circle, point moving on a circle. Not that exciting, but you'll see where it goes. You look at it from the side, it goes up and down, but it traces out a sine wave over time. Or rather, it's a helix in 3D. But you look at it from the side, it looks like a sine wave. So we can try and isolate one of those sections to try and play with it, and you write it down and you get a formula like that. And just to clarify, I throw in a lot of formulas on the diagrams to sort of explain what it is. I don't do this because I expect people to understand all of them, but rather as a sort of math immersion, like you have language immersion for learning. I think it's important to expose people to the fact that each one of those formulas and symbols has an interpretation, that it expresses an idea or a mechanism or an algorithm. How do we make this more interesting? Well, we can switch it to polar or circular coordinates, and then you get this nice little heart. You can repeat this 8 times around the circle, and then you get this nice little flower. And then if you're me and you're 17, you think, well, if I apply an arc sign, I can make those leaves pointy, and then you multiply it by the upside down heart, and then you get something else. And then you add a whole lot more math, and then you can stick that in your pipe and smoke it. Now the equation below there is the Navier-Stokes equation, is about 200 years old, I would say. And it's not actually still known if there's always a solution to it. So the kind of problems that drive these effects are quite complicated. And yet the implementation of this algorithm to animate the smoke and to implement the dynamics that are described here turn out to be quite simple, because it's a bunch of sort of simple pixel operations on a grid that are completely parallelized and run on the GPU. But what this play with math really emphasized for me was that everything in mathematics is a choice. When you learn mathematics in school, they set out this ladder of subjects in front of you and tell you to climb, 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 because A, you'll need it in real life, and B, for sure, there's a payoff at the end. And both of those are lies, because you don't really need anything other than simple arithmetic or geometry in practical life. But also there isn't really a payoff, because the same way there isn't a payoff for learning how to paint for most people. It's just a way to play around, to express yourself, to do something you find interesting. And so I kind of want to illustrate how that works. You take, for example, a rational function, which is a function that has x in the denominator, and when you graph it, you get what's called vertical asymptotes, where the values go off towards infinity, either positive or negative infinity. And we're told that at the point in the middle, you're dividing by 0. Dividing by 0 is undefined, so don't do it, because bad things will happen. But we can fix that. We really can. All you need to do is come up with a way of resolving that, what's called a singularity in the middle, which you can do, for example, with a mapping function. And it doesn't specifically matter which function that I'm using, because there's many different ones that you can use. All that matters is that it compresses the infinite range of numbers from negative infinity all the way to positive infinity into a finite range. And then you can take those numbers, wrap them around, and connect them. And when you do that, you find that you've created a continuous curve on the circular surface. And this might, it shows that you try different things, you apply different operators. Cool things happen, but not only that, but this is a mathematical concept called the projective number line that includes a point at infinity that is formalized, correct, you can reason about it, and it has applications. For example, in computer graphics, you use a lot of projective geometry, which includes points at infinity. And it's kind of, the mathematical version of what's called a vanishing point. When you do a perspective drawing, for example, you can see the point at infinity in your drawing right there, even though you could never get there. And that's kind of what mathematics allows you to do. It allows you to reason about things that are maybe impossible or impractical, and do so in a way that is formally, provably correct. And it allows you to do stuff like this. And if you then, for example, feed this into a GLSL shader and animate some curves and surfaces with it, you get cool little visual demos like this. And so this is something I just made while playing with that concept of projective numbers, just for fun. But it really is, for me, both, let's say, recreational and educational, because you really learn how the math works by playing around with the Lego pieces, putting them together in new and interesting and random ways, and just seeing what comes out the other end. So for the main part of this talk, I want to look at a couple of mathematical machines, show you how they work. They're pretty much just case studies, and there's way more things that I could talk about. So these are just a couple things that I find cool and interesting, and that I hope you'll find inspiring. So the first one is the Bezier curve. And the Bezier curve should be familiar to most people in this room. This is what you use when you use a pen tool in Adobe Illustrator or Inkscape or any of those programs, where you draw a curve by controlling the handles on the end. And usually in mathematics, curves are kind of scary. But in this case, actually, they're quite simple because you could construct a Bezier curve entirely with pen and paper. And that's maybe not that surprising when you learn that they were invented in the 1960s. And so it was Paul de Castrejou and Pierre Bezier, who worked at Citroën and Renault respectively, who were at the forefront of sort of these primitives, and led to the field of computer-aided design later. And you can see, given the designs of the time, why they might have been interested in designing curves in certain specific ways. So let's figure out how those work. But first, we need to talk about vectors. And if vectors is one of those words that sounds mathy and scary, we can swap that out with something else, arrows. Vectors are arrows, and when you do math with vectors, you're doing math with arrows. And so that means we need rules about how arrow math works. We'll start with identity. These two arrows, A and B, are considered the same. Why? Well, because they have the same length and they point in the same direction. So these two vectors are not the same. And when you have those two vectors, we can add them together like this, lay them end to end to create a new one, A plus B equals C. And we can do subtraction as well by turning a vector 180 degrees, and so again laying them end to end to turn C minus B equals A. And aside from regular arithmetic, we can also do scaling or multiplication. For example, A plus A is 3 times A to create a long vector B. And vice versa, you can divide B into 3 pieces to recover A from it, which is the same as multiplying by a third. And this theory of vectors or arrows is really all we need to know to start making Bezier curves. And what's better about this is that I haven't really said anything about how this might work on a computer or with numbers. We're literally just doing things with arrows on paper, and that's what kind of makes it interesting and fun to think about. So first we're going to make a line between 2 points, and we're going to use vector math to do that. But you may be wondering, if vectors are relative things, how do we identify points? Well, you pick an origin, and now you identify every point using the vector that connects it to the origin. So this is kind of position relative, position absolute from CSS, same principle. But it doesn't really, if you're going to implement this, you lay out a coordinate grid, and you have x and y coordinates in a certain scale, but it doesn't quite matter where this origin is, because the relative differences between your points don't change. And whenever you're doing anything with vector math, usually you don't even bother saying where the origin is, because the math doesn't change, or the outcome doesn't change, depending on where you put the origin. So in this case, to start making a line, we need to find the vector that connects the 2 points, which in this case is red minus blue equals green. And we're going to try and get to the points in the middle. And that's really quite easy, Because we can scale the green vector to, for example, 1/3 of its length, add that to the blue vector, and now we get the point that's 1/3 along the way. And this operation is called linear interpolation. The formula is there down below. It's often called lerping because it's like the I-18N of math. And it's an incredibly important and common operation. Whenever you're blending two images, for example, blending two layers in Photoshop, this is what's going on inside every single pixel. And any, tons of complex animations and even more complicated curves tend to come down to some sort of linear interpolation plus easing to make it happen. So let's make curves using this idea of lerping. First, we need to add a third point, which creates a second leg, a second line, and now we interpolate on that second leg as well. And we synchronize these two interpolations, so you get this nice sort of bouncy thing going. And when you have 2 points, well, it makes sense to connect them with a line and interpolate again. And when you do this, you get the quadratic Bezier curve. It has 2 stages of interpolation, has the 2 endpoints and 1 additional control point, and that's how it works. But this isn't the one that you commonly use in Illustrator or Inkscape, so let's figure out how to make that one. To continue, we need to add a 4th point, basically. So we add a 4th point with a 3rd leg. We interpolate again. And now we have 4 black points that are being interpolated into 3 purple points, 3 purple points being interpolated into 2 green points. And when you have 2 green points left at the end, well, it makes sense to connect them and interpolate again. And when you do this, you get the cubic Bezier curve, which has 3 stages of interpolation. So 2 endpoints, 2 control points, which means you can control the curve independently from both sides. And that's what makes it much more useful than the quadratic Bezier curve. And so when you're talking about vector graphics, talking about fonts, EPS, PDFs, this is pretty much what they're made out of. So Bezier curves are literally everywhere. These letters on this banner are Bezier curves at one point in their life before they were turned into ink on fabric. And so this whole construction of interpolation upon interpolation upon interpolation is what the curve is made out of, and it keeps on working when you move the control points around. And when you draw a curve in Illustrator, this is what's going on the inside. Now, the nice thing is that I said we're doing things with arrows on paper, but we really don't have to just stick to 2D, because all of this works perfectly in 3D as well. So you have control points in 3D, interpolations in 3D, and you can make curves that traverse 3D space just the same. And so if you're animating a camera through a space, you're trying to do a track and a pan movement or something, this is one way that you could do it. And curves, are interesting, but they're not that exciting. So we can go further. For example, you take a 4x4 grid of points, and you need 4 points to make a cubic Bezier curve, which means we can make 4 curves like this. We're going to be working in 3D, though, and I'm going to move those points up and down randomly a little bit to create some random curves. Now, we can start interpolating or running along the curve, again, in a synchronized fashion. And when you do this, you see that we get 4 new points. And when we have 4 new points, well, it makes sense to make another curve out of it. So we do that, and now you can sort of see it's starting to trace out a surface. So let's make that surface. And this is called the bicubic Bezier surface. And if you look closely, you can see that it's made out of cubic Bezier curves in both directions. It has 16 control points in total. 4 of those are the corners. The other 12 are floating around. The corners are fixed, the edges are Bezier curves, and everything in the middle is sort of a mix of the whole. And so these sorts of surfaces and constructions are what Pixar and DreamWorks characters are made out of, where you take a bunch of these tiny little patches and you stitch them together in a way that creates a continuous surface. And yet this complicated thing is really just made out of linear interpolations stacked in a specific way, and that's where the magic comes from. But every one of those little blocks there, whether they're blue or green, is doing the operation at the bottom, moving between 2 points. And that's how you make Shrek. I think that's cool. Now, the second thing I want to talk about is procedural generation. And procedural generation is basically any time you're trying to replace an artist with a piece of code, because usually that's cheaper. But not only that, games and CGI and 3D animation has gotten so complicated and detailed that you really need to automate your processes in order to deliver your game on time and within budget. And start with another quote. Inigo Quiles at Pixar, who said, "To make a film, we have to direct almost 200 billion pixels. That's a lot of mathematics." And so what he's talking about is you have an image like this that's obviously made out of over 1 million pixels. Each one of those has 3 colors, RGB. That's a lot of numbers. But you're not really trying to describe a formula that generates this image directly. What you're trying to describe is what's in the scene, the objects. For example, in this case, they were trying to generate moss on a computer tree bark, and they have a formula that describes the shape of every individual blade of grass or every leaf. They have another function that describes the density of moss on the surface. And so again, quite simple pieces, but combined in such a way that generates complexity of this level. Like pretty much all the foliage you see in this image was procedurally generated. And artists can just sort of control the placement of it. They don't need to control individual blades, because you wouldn't be able to tell the difference anyway. Now, procedural generation is very vague as a field, because, for example, visual effects, physical simulation is a way to procedurally generate things. In this case, fracture of glass and the dynamics of water. And another example is, for example, electronic music, which you could consider to be procedurally generated sound, either analog or digital. And many other things you can do. For example, generating cities procedurally is a classic sort of demo. And now you may be thinking you have no idea how you might start with something like this, but you do. Because if I gave you a sheet of paper and pen and I said, draw me a city grid and tell me where everything is, you could do it, because we all have a good concept, a good idea of what cities look like, where the parks should be, where the hospitals should be, where the highways should be. And so in this case, you can see they even built a logo into the street grid, because you can just do that. And once you have such a procedural generator for cities, you can generate infinite variations of the same concept really quickly. And that's what makes it cool. Now, you all, like I said, you know how to make a street grid if I asked you to, but you also know how to do this, most likely, because you did this in primary school, making paper snowflakes, where you fold a piece of paper, you fold it, then you cut some holes in it, and then you get this beautiful kaleidoscopic pattern. And what this person in the picture, who I'll reference later, has done is she's really copy-pasted and mirrored a pattern around the paper in a certain way using mathematical symmetries to save time and create a very accurate replica and create something that looks cool. Now, I'm terrible with paper in my hands. I do software. So my version of this is slightly different. My question is, what does it look like when you fold space? Because 3D is more interesting than 2D. And when I say folding space, I don't just mean folding space in a simple way, but folding space in any mathematical way that we could. And it turns out you end up with some really interesting things. I didn't invent this. They're called hybrid fractals. And they look like this, at least if it's working. And so what you end up with is a 3D shape in space of incredible complexity and this is the result of folding space 15 times and then cutting out everything except a cube and a cylinder running through it. You can sort of see that pattern repeating everywhere. And so whenever there was a folding of one side on the other, that's where you get sort of a reflection, just like you get a reflection in the paper snowflake in the pattern. This one's kind of creepy, but we can make cheerful ones too. call this one bananas. This is a donut with a cylinder running through it that's been cut out, and again, folding space about 15 times in slightly different ways. And you end up with these mind-bogglingly complicated shapes that sometimes stretch on forever, but certainly stretch on far enough that you take a while to reach the edge. And despite the fact that there doesn't seem to really be a completely consistent structure to it, you can still see that there's patterns, there's order, and it just looks cool and crazy. And so this is kind of what happens when you put mathematical Legos together, because this is 15 different ways of folding space combined, and out comes something that certainly looks a lot more complicated. This is what the inside looks like. Another example. So the JS1K demo that I started out with the the purple and yellow, I've simplified it and I made a diagram out of it so you can show how it works. Because I want to deconstruct this and you can see that the magic in that demo is really not that magical. So what this demo does is it animates a bunch of tendrils on a sphere. And it looks dense and confusing, and you can't really quite see what's going on. So if I isolate one tendril, it looks like this. And you can see that it's really just a point that's moving on a sphere that's tracing a tail behind it. So let's figure out how that works. First, we need to unwrap the sphere. So we do that. And this is mapping coordinates on the sphere to latitude, longitude, which is called the spherical coordinate transform. You can look at the formulas. And there's nothing special about that. And the height on the sphere, sort of away from the gravity well, as Andrew was just saying, is the third dimension away from the grid. And the blue curve is the tendril that's sweeping around. Now, it almost looks like there's some sort of physics effect going on to make it sweep around, but that's kind of an illusion, because if I extend the tendril, you can see that it's sort of just coming out of the wall. It's being extruded. There's no dynamics on the curve itself. And that means that the question of how do I make these crazy things fly around the sphere has been reduced to two things. And that's, one, the longitude component, which is the x in this case, I think. And the other is the latitude component. And now the question is, how do we calculate these things? And the answer is you throw together a bunch of random shit. There's no structure, no rhyme, no reason to this. It's just a bunch of random mathematical Legos that I plug together in such a way that on one end you plug in time, on the other end out comes longitude, and similar for latitude. And the numbers in the boxes in these formulas are sort of the constants that you can tweak and tune to get different effects and different shapes out of it. Now, to explain how this works, because it seems like black magic, right? Like you have no idea why combining certain effects, certain functions should result in a certain output. But there's a couple ways to think about this and make sense of it. And it really all comes down to the variable x. X is the bane of many students' existence. And quite often we're told x is the unknown number, the solution to be found. We just don't know what it is yet. But I find it's better to think about x not as the unknown number, but all numbers. X is a placeholder. And we want to know what happens when we plug every possible number in there and what comes out of it. And that might seem like it's really hard to think about, but it really isn't, because all you need to do is graph the input and the output, just like this. And in this case, this is the function that does nothing, just returns x, which looks like a diagonal like that. And this is important because this is the neutral position. And everything else that you can do to x, you have to consider relative to this diagonal. Now, in mathematics, you're working with real numbers, so we can have any number in between, not just the integers, and when you write it out, it looks like that. And now, the point is that anything you do with your formula has a certain effect on the graph that's predictable, that's understandable, and once you sort of develop a mastery of this vocabulary and grammar of operations, you can really sculpt the math with high degree of control. So that's kind of what I want to show you. So fx equals x look like this. If you just replace it with a constant number, you get a horizontal line. That's not very interesting. If you replace it with 2x, you get a line that has twice the slope. You add 1 to it, it shifts up by 1. And that's not all that interesting. Here's where the magic begins. If we take the absolute value, now all the negative numbers become positive. And when you think about it, what this is doing is folding the bottom half onto the top. And so we can keep doing this. For example, move it down by 4 units, fold up again, and now we've created creases like that. You can do that again, move it down, fold it up again. And now imagine, for example, that we start cutting out numbers. For example, all the numbers between 1 and 2. We want to eliminate that part of the graph. And you see that we've created 7 holes in the graph now by making a single cut, just like you create holes in the paper snowflake after you folded it. And this is the mathematical version of that, and this is the basic principle behind how those crazy 3D fractals get created. Now let's look at something else. This is, for example, an arctangent that I've scaled up a bit. And again, it doesn't quite really matter what this is for, because we're just interested in what it looks like. This is kind of the luxury of when you're playing with math, is that you don't need to do anything right. You could just do what's interesting. And so when you apply this function, the effect of that is visible when you compare it to the diagonal, to the neutral position that I just mentioned. And you can see in the middle, the values get pulled outwards, either more positive or more negative, depending on their sign. But beyond a certain point, they get folded in, or pulled in. There's not so much a fold, because the function still rises and always rises. It never goes down. And what this function does is it actually maps every number such that it never goes above 4 and minus 4 in this case, which means this is a mapping function that you could use to get rid of your dividing by 0 and your infinities. The one I used was very similar. Not exactly the same, but same principle. What else can you do? Well, playing with formulas like this is really like, blending layers in Photoshop. Because, for example, you could take a sine wave and add that to the arctangent, and then you get a Ripley wave that follows the curve of the arctangent. But there's another way to look at this, is that the sine wave was shifted up and down to follow the curve of the arctangent. And the two sort of visualizations really reflect the fact that a plus b is the same as b plus a, at least in most cases, but you kind of don't want to deal with the cases where that's not true. And you can do other things, just like you have blend modes and layer blend modes in Photoshop. You have different operations in mathematics that have different effects. For example, multiplication. Now, you may be thinking that this is going to lead to a system where you have one formula to rule them all that has to somehow coalesce into a perfect, like the Zoidberg curve that you may have seen on Wolfram Alpha, or the psi curve, the Korean dancer. But those are exceptions. That's generally not how we work. Because you have a lot of control. For example, if you apply a minimum and maximum operator to x before you plug it into here, you get this, which is what's called a window function, because it's 0 everywhere except into a small window in the middle. And on top of that, it's nice and smooth and continuous, which is good. And now you take another curve. For example, here I have this green moving thing. We'll go into what that is exactly, but right now it's just a thing. You multiply it by this window function, and now you get this sort of section of curve that we can tune and change in the middle, but that's 0 everywhere else. And that's nice because you can use this as a brush. For example, you take 3 of these things. One has been made negative, the other has been stretched out horizontally and kind of compressed vertically. You add them together, you can see that you've sculpted this nice little landscape. And you don't really have control over what the individual curves are doing beyond tuning the knob on time in this case. But you can move them around and have control over the end result. And so this is a way that procedural generation can be used not to replace artists, but to make them more efficient, to allow them, for example, to create vast landscapes with just a click of a button, and then just start sculpting certain areas a little bit so that, this is where the skull fortress of doom is going to go. So we need a little nice outcropping so the lava can pour down tastefully. You know how it goes. Now this is all in one dimension, and so curves might not look that interesting, but so I'd like to show you how you can apply these things in higher dimensions. For example, 2D. In this case, I have a patch that's spanned between 4 points, and you might think this is very similar to the bicubic Bezier surface that I showed before, only these points can only move up and down, because this is a function of two variables, x and y, that maps onto the height above the grid here. And what we're going to do is we're going to use the cosine window of before, but I'm going to center it on one of the corners like this. And because it's a two-dimensional cosine window, you can imagine it's like a circular cosine bump. In this case, I've isolated one quadrant of it around the corner. And if you do this for all 4 corners and you give them different heights and you add them all together, it looks like this. And so you can see that we've basically created a new sort of primitive, in this case cosine interpolation, where we have 4 values that we can control to create a little curved patch in the middle. Now what can you do with this? Well, you take, for example, a grid of these things. By default, they're not going to line up. It doesn't look very good. But if you instead equalize the heights at all the corners, it matches up automatically. And this is one of the things that's nice about cosine interpolation is, like I said, it was smooth at the edges, which means at every corner of a patch, the surface is always perfectly horizontal, and that's what makes it easy to match it up. And so this is one level of value noise with cosine interpolation. If you want to be precise, we can create an additional one with a higher degree of division. So instead of 2 by 2 patches, this is 4 by 4. Again, you make them match up, and you get a nice continuous surface. And we can do that again at a higher level of division, 8 by 8, and so on. Now, individually, these things don't look that great. They look artificial. And you can see that the amount of variation has a sort of relative, a sort of constant scale. The bumps in every one of these 3 surfaces are of a consistent size because of how it was generated. But if you start adding them all together, so this is level 1, I add level 2 to it, level 3, level 4, level 5, so 16 and 32 divisions, you end up with something quite different. It looks like a rocky, craggy mountain landscape. And this is called layered or stacked value noise, and it is a very old technique. I mean, this stuff goes back to late 70s, early 80s, I believe. And there's many more sophisticated ways of doing this that have much more natural appearances. But I like this example because it's quite simple. The operations involved are quite easy, and you can visualize it so well and see that by combining simple elements, you get something that looks far more complicated than it really is. And these sort of techniques were actually used by Spore, the Maxis game. It's probably the best commercial example of procedural generation put in action to make these sort of fantasy planets with crazy candy cane volcanoes and other things. Again, the brushes were designed by artists, the shapes, the individual things that you can stamp onto the surface, but the placement of the brushes was determined by algorithms. And they used similar principles to create animal patterns on the creatures that you create in the game. And it's really quite fascinating how they did it. The game itself was maybe not that great. And so I saw this technique, and I wanted to make, I don't know why my videos are kind of failing. There we go. Wanted to make my own version of it. And so this is pre-recorded. This isn't WebGL. This was Ogre OpenGL. And, but applies this principle of sort of fractal levels of detail, or just adding additional levels of detail to create natural-looking rocky surfaces, in this case an asteroid. It does have, those lines running across, which are actually rounding errors that I didn't get around to fixing. Here I put in a giant crater. There's tons of detail here, really. You can keep on zooming in. It's doing sort of a Google Earth effect, where it just generates new tiles on the fly as you zoom in. And the only limitation in this demo was the memory on the GPU to store the tiles, because if you had unlimited memory, you could keep on zooming in and go down to ridiculous levels of scale. Now, finally, I want to talk about physics and physics engines, because they're really just fun to play with. So you take this arrangement of circles and blobs that doesn't look that great until you add physics, and now they bounce. And now I can invert gravity, stick to the ceiling, let them fall down again, get them up again, down again. And there's something going on here, and I have to time this right. That's called the Brazil nut effect. And you may have noticed this if you buy a bag of mixed nuts, somehow the Brazil nuts always end up on top. And you know, I don't like Brazil nuts. That sucks. And this physics engine somehow replicates that effect automatically. I didn't teach it to do that. All I did was implement the equations of motion. I implemented collision, and somehow if I shake up this box enough times, all the big circles end up on top, just like they do in reality. And so it shows the emergent properties of physics engines, where you implement simple behaviors and suddenly complicated things happen. Now, what I'd like to show you is how a physics engine works. Not necessarily because I think everybody, should be able to write a really good physics engine by heart, because that is hard. But making a simple physics engine is quite easy, and it teaches you a whole lot about how the mathematics work, how vector math works. And so if you're ever trying to do something with physics in a game, I would recommend you use something off the shelf. But if you're trying to get familiar with the mathematics, I would recommend you try and write your own physics engine. There's tons of material online, and it really teaches you a lot in doing so. So how does that work? Well, every physics engine basically has two things in it. Or it has knowledge about the world, which usually is where is everything, which is a position of your particles or rigid objects or fluids or whatever you're trying to simulate. And position is a vector. That's not surprising. Second, we have velocity. And the fact that velocity is a vector might seem strange, because speed seems like it should just be a number. But the reason this is a vector is because you want to know where something is going as well as how fast it's going. So that's what makes it a vector. And the purpose of the physics engine is then to say, if this is the situation that we started out with, what's it like in the future, which in this case we can find just by adding the velocity to the position to get the position 1 second into the future. And the reason we can just add the velocity to the position is because we're assuming the velocity is expressed in units per second, for example, meters per second. If you wanted to find out what the situation was like half a second in the future, it's quite easy. You scale the green vector to velocity by half, you add that to position, and now you get the position 1.5 seconds into the future. And if you do this with small enough time steps, you get an object that moves. And you can see that I've implemented a simple collision on the edges. Usually, collision is quite a hard problem with a capital H, but in this case, it's quite simple, because all I'm doing is reflecting the velocity horizontally or vertically whenever it touches the edge. And that's how you make simple dynamical systems with motion. But in reality, objects have forces applied to them. Things tug on other things. So we rarely get objects moving in straight lines. We need to figure out how that works. So we start with the same situation. We have a position and a velocity. But now we also have a force. Or rather, we have an acceleration. And as we saw with the accelerometer in the phone and the iPad, acceleration is an expression of force, but because of Newton's laws of motion, you have to divide force by mass to get the acceleration. Because if you apply the same force to, say, a tiny marble or a giant car, obviously the car isn't going to move quite as far. So that's Newton's third law of motion, I believe. And that's why we talk about acceleration and not force. So how do we incorporate acceleration into this model? Well, remember, vectors are relative things, so we could move the red vector around as much as we like without changing it. And we'll put that there because it makes it easier to see what's going on. So to move the position into the future, we do the same thing we did before. For example, here I'm moving 1/3 of a second into the future by adding 1/3 of the green vector to the blue vector. But now we do the same to the green vector by adding 1/3 of the red vector to the green vector. And this looks kind of jumbled, but remember, we can move vectors around. So this is the same situation as that. And it may not look like it, but we've already created the physics engine. Because if I continue this process, advancing by little time steps, you can see that this traces out an arc, just like a ball would when you throw it in a gravity field. And if you do this with small enough time steps, you get something that bounces in a way that's physically correct. And all you need to do to make these sort of models work is to incorporate the appropriate physical law in this, whether it's gravity or something else. And out comes a physics engine that seems to have the right emergent properties. For example, springs. Now, springs are governed by something called Hooke's law, which means the amount of force that the spring exerts to try and, when you disturb it, is proportional to how far it's been pulled away from its equilibrium. So, for example, give this a tug, it's going to start doing this, where the force and the acceleration, which is the red arrow, is directly proportional to whether the spring is extended or compressed. The red vector tugs on the green vector, which is the velocity, and then the green vector tugs on position, which is the 2 points at the end, and out comes the spring that bounces. And now, everything that we've done so far has been simple adding and multiplication of vectors. There's nothing complicated, nothing more complicated than that going on. And yet, if you were to graph the motion of the spring, you would find that it describes a sine wave. And this is another example of the emergent properties of physics, where by just putting together very simple rules, somehow we create things that do a lot more complicated things than we might expect. So for example, you put a bunch of these springs together, and in this case I've just drawn them as lines. It simply does the right thing. And I give it a nudge, it flies up and bounces, smack it against the wall, it just works. So that's, in theory, how you make a physics engine. Unfortunately, in practice, there's a little bit of a problem. Because I said, if we do this with small enough time steps, you get smooth animation and smooth motion, and it's kind of implied that that will give you the correct physical result. But it's not quite that simple. Suppose, for example, we have Earth orbiting the Sun in a circular orbit, or almost circular orbit, and it has a velocity like this that's tangent to the circle. And so if we start to do the physics integration that we just did, you add velocity to position, you find that you completely step off the orbit of the planet. That's wrong. And if you keep on doing this, your planet spirals outward, which means your solar system flies apart and everybody dies in the cold vacuum of space, which is not good. And you can try and mitigate this by reducing the time steps, which works a little bit, but it doesn't make the problem go away. It just reduces it. And not only that, this is one of those big O notation things where if you want your error to be 10 times smaller, you need to take steps that are 10 times smaller, which is generally not good enough, because you're just going to spend so much time taking teeny tiny little steps to try and reduce the error that it's taking forever to simulate. And in fact, it seems like the only way that you could avoid stepping off the circle is if you take infinitely small steps. And that's the domain of calculus, which involves lovely looking things like that, and involves more complicated solvers, basically, in practice, that reduce the error in certain ways and have formulas that you can look up. For example, Verlet integration or Runge-Kutta methods, which have different big O levels of performance. And unlike big O(n), which you may be familiar with from computer science, in this case, the higher the power, the better, actually, because it means you're, and if you make your time step 10 times smaller, in the second and third case, you're going to get a factor of 100 or a factor of 1,000 improvement on your error. And so that's pretty much physics engine in a couple minutes. Finally, I just want to show you some sandboxes and toys that you can go and play with, because as I try to emphasize, play is what makes math fun. And there's a bunch of interesting tools at your disposal. For example, Grapher.app on OS X. This is included with every Mac for free. It just sits there in your utilities folder, unloved, alone, crying. And it's an amazing program. It does mathematical typography, it does 3D graphs. This is the red and yellow swirly curves with the infinity point prototyped. This was how I came up with it, and then I just copy-pasted those formulas into GLSL. Another one, mandelbulber.com, is a 3D fractal explorer that's cross-platform, allows you to create all those crazy 3D fractals that you've seen. GLSL, Sandbox, and Shader Toy are two WebGL playgrounds that you can play with code online, share code online, look at examples that other people have made. Processing, or in processing.js, which is the JavaScript version, is a platform that allows you to work with dynamical systems. But it really doesn't have to be graphical. You could do web audio, you can work with AI, you can make games and puzzles. And not so much the graphics, but the logic behind the games is often mathematical in nature too, and because you're designing a system that has to respond to anything the player can do. And trying to do this completely ad hoc is not really the best way to go around this. You need to reason formally about everything that they could possibly do. And outside that, there's 3D printing that you can do, making 3D models, programming Arduinos, whether it's reading a sensor and processing that data, or feeding a motor, an actuator, or something like that. That involves mathematics in every aspect. Finally, some references, just things to look at. Natureofcode.com by Daniel Schiffman. This is an amazing ebook that pretty much does what I just did, but way more thorough, and covers way more topics. Has tons of examples in processing. It's incredibly polished, incredibly well made. I highly recommend that you look at it. The YouTube channel Vihart, who is, she has a series called Doodling in Math Class, as well as other videos. For example, making hexaflexagonal tacos, which somehow fold up and then the guacamole disappears. And she really does amazing things and has an incredibly playful way of going about things. And incidentally, her father, George Hart, was the person who spearheaded the Museum of Mathematics, I believe, in New York, which is an amazing place that opened last year. It takes a similar approach to mathematics. Kill Math by Brett Victor, so one of the people whose quote I used, and whose talks you should generally all watch because he pretty much does magic for an hour in the most amazing, mind-blowing way. And betterexplained.com, which is the math textbook that you wish you had, that has better explanations of linear algebra, exponentiation, and then all the other sort of high school math that they managed to make boring and dull and lame by baking it into symbols and telling you to memorize them. That's pretty much all I have to say. I have more stuff like this on my website. The slides that you've seen today were almost all rendered live with something called mathbox.js. And I hope you enjoy it. Thank you very much.